All right, so this tutorial we're going to look at Isaac Newton's universal law of gravitation, one of the greatest achievements in the history of human thinking, science, etc. As we mentioned in class, Newton's ideas of gravitation, which united the laws of physics on Earth to those of the heavens, had a profound effect on the next century of thinkers. And it is a valid theory, even though it has some flaws that Einstein exploited about 2 centuries later. It's still taught today because it works very, very well. So what we want to do is establish essentially what factors give rise to the pull of gravity on something, and how can we calculate the pull of gravity in the most universal sense. Right now we can calculate gravity by using the equation F of g equals mg, but that's because we know the value of little g, the acceleration due to gravity on Earth. If we were to go to another planet, little g would be different, and so we wouldn't be able to use that simple equation. We need a more universal idea. Okay, so let's just jump right into it. Basically, Newton had the insight, without necessarily any proof or experimental data, that the force of gravity exists between 2 or more bodies that have mass. Okay, so mass is the key. All right, anything with mass, big or small, has a gravitational pull of gravity, and it's always attractive. All right, so the Earth attracts all of us to it because, well, it has a huge mass. But by the same token, since we have mass, we attract the Earth, or we attract each other. The force of attraction amongst us in a classroom or anywhere else is obviously very, very, very weak because we never really actually feel the physical gravitational attraction. And so that's something we'll visit later, but next time think about why we don't slide across the room on our desks, and because of that physical attraction, because friction is overwhelming it, and friction isn't that strong in this case. Okay, there's another fact that matters. So if we look at the diagram where we have 2 objects, mass 1, mass 2, they could probably represent the Earth and the Moon, the Sun and the Earth, or any 2 bodies that are separated by some distance. He's basically saying that the force of gravity is due to the mass of the one and the mass of the other. They're both pulling on each other. Okay. And then another fact that matters is the distance between them. So if you notice on here, we've got a distance r from the center of each mass. And so when we measure distances between bodies, it's always from the center of one to the center of the other. We never do surfaces. Newton had used integral calculus to show why treating the distances from center to center was a valid way of understanding extended mass, but that's not something we're going to worry about. And what he found, and this was the most convincing part for other people, is that the force of gravity is inversely proportional to the square of their distances. Again, those distances are from center to center. So basically what we can do is make not quite an equation, but a proportionality. He's saying anywhere in the universe, if you want to talk about the force of gravity, it's proportional to the product of the 2 masses divided by the square of their distances. And this is called the inverse square law. And so I want to take a few minutes to show you how we can use this before we turn to the idea of an actual equation. So note, this is a proportionality. It is not an equation yet because we're missing something. But for right now, this is good enough to do some very interesting physics. So before we move on, let me reiterate. Any object in the universe with mass will attract another object in the universe with mass, with the force proportional to the product of the masses, not the sums, and the distance inverse relationship to the square of the distances. And that squared part is going to play an important role. So the further away you get from a body, the weaker the force of gravity is, which kind of makes sense. But the inverse squared means that if you double the distance, it's not going to be 2 times less, but 2 squared times less, or 1/4 the force. So what evidence did Newton have that the law of gravity followed the inverse square law? Well, he actually used evidence from the moon. So it's a very, very clever experiment. All right, so imagine, let's just draw the Earth right here, and we're standing on the Earth. Highly exaggerated. And then let's say the moon is up there in the sky. Okay? Now, it was known at the time, not necessarily in meters, that the moon was a certain distance away. It turns out to be 3.84 times 10 to the 8th meters away. And Newton didn't have that number because the meter hadn't been invented yet, but he did know that the moon was roughly 60 Earth radii away. So let's put that in context so you understand this derivation. So if we take the center of the Earth right here and we go to the surface of the Earth, we would say we're 1 Earth radius away. Okay, so when you're standing on a surface, you're not 0 distance away, but you are 1 Earth radius away from the center. And so it was known that the moon was 60 Earth radii away. Alrighty, so according to Newton's idea here, if the moon is a lot further away, then the pull of gravity on the moon would be less than the pull of gravity on us. So we'll come back to that in a second. Now, another important piece of information is known is that the period of the moon, the time it takes to go around once, is roughly 27.3 days. But in terms of seconds, if we convert that to seconds, we have 2.36 times 10 to the 6 seconds. All right, so how can we use this to verify his idea of the inverse square law? If the moon and we are pulled to the Earth because of gravity, then we should feel an acceleration due to that gravity. Now, we know that the acceleration due to gravity when you're at the surface of the Earth is 9.8. All right? But what would be the acceleration of the moon as it goes round and round the Earth? Well, we can't just do a kinematics problem, but we can use the idea of centripetal acceleration. So we know that centripetal acceleration, A sub c, equals 4 pi squared r all over t squared. In other words, if we know the distance the moon is from the Earth and we know the time it takes to go around, we can calculate this fairly easily. So if we plug in the numbers, and I'll leave that to you to plug them in, we find that the centripetal acceleration of the moon around the Earth is a very small number, 0.00272 meters per second squared. Okay, so now we can set up a proportion. What he's hypothesizing, if you will, is if the moon is 60 times further away than the Earth, then the acceleration due to gravity of the moon in regard to the Earth should be a lot smaller. And according to this hypothesis, if it's 60 times further away, then if the acceleration due to gravity is proportional to the force of gravity is inversely proportional to the square of the distance, then the acceleration due to gravity of the moon around the Earth should be 1 over 60 squared less than that of the on the surface of the Earth. So if we take the acceleration of the acceleration of a body near the Earth, that's 9.8, and divided by the acceleration of an object at the moon's distance, which is 0.00272 meters per second squared, sure enough, we get that to be very close to 3,600, which is 60 squared, or I should say, yeah. So 3,600 is 60 squared. And so he had some very good evidence that his idea of the inverse square law was valid, and people took notice of that. Okay, now here's a neat application we can use with the idea of proportionality. Okay, we can apply it to all the other planets of the solar system, and that if we know how big they are in terms of mass relative to the Earth and their size relative to the Earth, we can figure out what the pull of gravity will be on that planet. So here is the idea. If we've got some planet right here, which is called planet X, and we have, again, a person standing on it, or an object on it. Okay, in this particular problem, I just put a 1 kilogram object on the surface of that planet. Okay, so there's our object. They are a certain distance away, which is essentially the radius of the planet, and they each have a mass, m1, m2. So Newton is telling us that the force of gravity between those two bodies is proportional to their respective masses divided by the square of the distances. Okay, so let's take the Earth, for example. If we, instead of giving the actual mass, we call its relative mass, it's 1 Earth's mass and it's 1 Earth size, then according to this proportions, if I bring my 1 kilogram object to that, okay, my proportion will be 1 kilogram times 1 Earth mass, which I'm just going to put 1, all over 1 squared. That's how far away we are from the Earth, and I get 1. So my weight is going to be my normal weight. It should be 1 kilogram. So my weight would be 1 times the normal weight, which would be 9.8 newtons, and my acceleration due to gravity, we already know, would be 9.8 meters per second squared. So let's see what happens if we go to a planet like Mercury. Okay, so if we go to a planet like Mercury, and I'm looking at the proportions, I see that, all right, Mercury has 0.055 the mass of the Earth. So for one of the masses down here, I put 0.055. That's its relative mass of the Earth, multiplied by 1. That's the mass of the object we're bringing there. And then we divide it by how far away we are from Mercury's center, which is 0.38 that of the Earth's radii. So I can put in 0.38, but I have to square it. That's really important. And so if I look at the proportionality that comes out of that, it turns out to be 0.38. Coincidence, that's the same as radius. So what we're saying is that on Mercury, you will weigh 0.38 that of the force of gravity on the Earth. So if you weigh 9.8 newtons on Earth, on Mercury, you will weigh 3.7 newtons. And if the acceleration due to gravity on Earth is 9.8, on Mercury, it will be 0.38 times 9.8, which of course is 3.7 meters per second squared. So you're roughly 1/3 the acceleration due to gravity on Mercury. Okay, so what I'd like you to do is try to do the rest of these right now to give yourself practice. So I'm going to pause it, and then I'm going to start it again in a few seconds. All right, so up here on the chart, you can see the answers for the proportionalities for the 4 other planets. All right, if you didn't get these values, please try it again, and then you can just multiply the each of these numbers by the normal weight, 9.8, to get the other 2 columns. Okay, so some things to point out. Venus is often called our sister planet, and we can see why. It is roughly the same mass, roughly the same size, and therefore the pull of gravity on Venus is very similar to Earth. Jupiter stands out in that the pull of gravity on you is 2.5 times greater, and that's primarily due to its huge mass compared to the size. On the other hand, Saturn, which is the second largest planet in the solar system, has almost 100 times the mass, but because its size is relatively large for that mass, the pull of gravity on Saturn is just barely that greater than Earth. Okay, so it tells us that Saturn is not a very dense planet, even though it's a very, very massive planet. So what I want to finish up this tutorial is the last stage in understanding universal gravitation. Okay, in that we are left with right now the idea that the force of gravity between any 2 bodies is proportional to their masses and inversely proportional to the squared distance. But Newton was never ever able to turn this into an actual equation because he could not ever determine the proportionality constant that was needed for this. Okay, so what am I talking about? Well, if I were to take 1 kilogram mass and take another kilogram mass and put them 1 meter apart, okay, and apply this as an equation, I would get a force of 1 Newton. Okay, well, actually, let me take that back. I would not get a force of 1 Newton, but rather, if I looked at the units, I would see that it's 1 kilogram times kilogram divided by meter squared. Okay, so that's not a unit, a unit of newtons, where we're expecting to get units of newtons. So that tells us that we're missing something here for the units. And also, if I took a kilogram and a kilogram and put them 1 meter apart, 1 Newton would be way too big. If we hung them from strings, we would see the strings start coming together, which we don't see. So it tells us the force of gravity between 2 1 kilogram objects that are 1 meter apart is much less than 1 unit. So what we need here is a proportionality constant to get our units right and to calibrate the strength of gravity to our system of units that we've developed. So that's something we can talk more in class if that's confusing to you. So in order to come up with this value, this constant, you have to do it experimentally. And Newton did not have the means to do that at the time. Okay, so we're talking about this proportionality constant. And I shouldn't have put a K there. It actually turns out to be a big G. Okay, so let's try to finish this up. It took about 100 years, a century, for a guy named Henry Cavendish to do one of the most famous experiments in all of physics. One of the most difficult experiments ever done. Even today, it's a very difficult experiment to do. He derives the value of the universal gravitational constant, big G. All right, I'm going to talk more in class on the details of this, and I'll explain to you how one might go about finding G. But let me just give you the results. He found that the value of G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Okay, this is called universal gravitational constant, meaning it's the same value for all situations. Do not confuse this with little g, the acceleration due to gravity on a particular planet, which changes from planet to planet. Big G is universal, It's the same number. So now we can make an actual equation. It says the force of gravity between any two objects in the universe is equal to big G times the product of the masses divided by the square of their distance. And this is an absolute equation. If I ask you to find the force of gravity